Hey guys, so we are kind of continuing along with our discussion of chemistry and water, and this is basically going to be talking a little bit about solubility. So the last thing we talked about was, this guy right here, kind of telling us how things dissolve, and we talked about the water molecule dead polar bears initiating particles into solution, as it were, the polar bear beatdown, right? So today we want to kind of expand on that idea of dissolving substances in water and what that does to the resulting solution. So first, we want to talk a little bit about how things get in water, or what are the factors that affect solubility. Now, solubility is just the ability of a solute to dissolve in a solvent. So remember, when we talk about a solution, we have the solute, we have the solvent, and then we have the solution. The solute is the thing that gets dissolved. The solvent is the thing that does the dissolving, and then the solution is the result of the solute-solvent combination. Remember that solutions are mixtures. They are physical mixtures. They're not chemical mixtures, so they can be separated by physical means. That was a lot of information. Let's talk about what are the factors that actually affect solubility. So I always tell people we need to think of this in two different ways. Number one, think about your sweet tea. I'm talking that nasty, disgusting Chicken Express sweet tea where you got so much sugar in there that it's just disgustingly gross. I don't know how people drink that. My wife loves it. I can't stand it. It is way too sweet. And then I want you to think about your Coca-Cola, frosty Coca-Cola beverage, okay? And that's going to give us the solubility rules for solids, because we're dissolving sugar in tea, right? And then it's going to give us the solubility rules for a gas. We are dissolving the fizz in a Coke. That's what makes a Coke taste so good, is that carbon dioxide fizz, right? So let's think of sweet tea and let's think of fizz. So let's look at the factors that affect solubility. And if you notice, this dude looks like he is taking a shower on a nice hot afternoon, a little pigeon bath. He is hot, right? And so heat is going to be the first factor that affects solubility. Now, for a sweet tea, we know that if we want to make sweet tea, the best way to make it is to heat up water, add the tea bags, that brews the tea. Then before you go throwing ice into it, you want to put the sugar into the hot tea because it helps it dissolve faster. So for solids, it's going to dissolve faster, or it's going to increase the solubility, okay? So if you're keeping track of that, I would maybe make a note out to the side. Increase heat equals increase solubility of solids, right? Then for gases, let's look at that Coca-Cola frosty beverage. Do me a favor, close your eyes, pull the pop top. That's the sound you get right now. That sound you get is the deliciousness of fizz or carbonation in your soda, right? So let's set that Coke on the countertop on a nice hot summer day, and let's wait about 20 minutes and let's come back and drink that Coke. Does it taste as good? Your answer would be no. That's because it has started to heat up. When it starts to heat up, you see bubbles leaving faster. That means the bubbles are not as soluble. So when we heat up the solution, that is actually going to decrease the solubility of gases. So for gases, increase heat, decrease solubility of gases, right? Then let's keep rolling here. The second factor, if you don't know this guy is nicknamed the Crusher because he crushes things, right? So if we had a cube of sugar, so looking at the sweet tea one, if we had a cube of sugar versus powdered sugar, which one would dissolve faster? You should have known this since like first grade. Basically the one that you crush up should dissolve faster. Now what are you doing when you crush that up, you're actually increasing the surface area, right? Don't look at the shake it up picture yet. You're increasing the surface area of the sugar, right? And by increasing the surface area, water can now get on more surfaces and pull that molecule apart. So surface area will increase solubility. So if we increase surface area, we increase the solubility of solids, right? Then as far as surface area for gases, this is a little bit different. You can't really crush a gas, but what you can do is make the bubbles a little bit smaller, which if the bubbles are a little bit smaller, they will dissolve better. So here, I'm not going to really get you too much on this one, but if you increase surface area, you will also increase the solubility of those gases. But really there's one that's a little bit more at play later. So surface area doesn't affect gases as much. So the next one was looking at the shake it up. I forgot to go over that. Looking at shake it up there. I think that's the Miley Cyrus Disney something or other from years ago. But anyway, shake it up, that show, shake it up. If you shake something up, we're going to call that agitation, right? And agitation is just stirring or shaking. So if we were to stir or shake that sweet tea mixture, so talking about solids again, stirring and shaking will increase the solubility of that as well. So increase agitation, stirring or shaking, equals increase in solubility of solids. For gases, if you take that Coke and you shake it up, where does the fizz go? It's going to leave, right? So when you increase agitation of gases, you decrease solubility of those gases. They want to leave the solution. Now, there is one really big exception to this, and that is going to be oxygen. Oxygen is a gas that loves agitation. Whenever you agitate water, so you start shaking up water, that will actually help you introduce more oxygen into the solution. So oxygen kind of goes against the grain. If we add some agitation, oxygen likes to go into solution. So put a little asterisk by that rule for gases. Normally if we increase agitation, we decrease the solubility of gases. But in this case with oxygen, you increase the solubility of oxygen. That's really important, especially if you are a fish and you need to live. Now that last picture there, that looks like a fancy schmancy cooker, has a screw-on lid, has a little pressure gauge on it. That's called a pressure cooker, right? So pressure is going to be the fourth factor that really affects solubility. For solids, this isn't going to play into it as much. We can't really compress solids anymore, so pressure doesn't really do much. But for gases, this is going to be really important. If you add pressure, so you take your Coca-Cola beverage, if you want it to stay good longer, you want the bubbles to dissolve better longer, right? Then you screw the cap back on and then you put it in the fridge, right? So putting it in the fridge lowers the heat, which keeps the gas there. But then screwing that cap back on also allows pressure to build back up. And at some point when pressure builds up to a significant amount, bubbles will no longer leave the solution. They'll actually stay in the solution. So if you can pressurize that solution with gas in it, then that will actually increase the solubility. So if we increase pressure, we increase the pressure or the solubility of gases in solution. That's pretty important if we're talking about atmospheric pressure. For example, there's not going to be a huge difference in the two, but when we start getting down into the ocean depths, pressure is pretty great there, so it's hard for oxygen to stay in solution there. But we'll talk more about that later. So here is our general rule in regards to temperature. You'll probably see this graph again just to see if you know how to read graphs. But basically, if you notice, most of these solids, and that's most of these solids tend to go up in solubility as temperature goes up. Notice there are some exclusions to that rule, right? So we always have exclusions to the rule. But in the case of gases, notice that as we increase temperature, we decrease the solubility of gases. So again, there are some exceptions to that rule as well. One of those will be carbon dioxide. Actually, not carbon dioxide, I'm sorry, scratch that. But there are some exceptions to that as well. But those aren't as important as some other things. So just know that the reason I showed you this graph is really for most of the stuff, whatever you do to the factor, whatever it does to solids, for the most part, it's the opposite for gases, right? So in this case, as temperature goes up, solubility goes up for solids, but then as temperature goes up, solubility goes down for gases. So let's take a look at that real quick. Two gases, pretty important. First is going to be dissolved oxygen. All right, organisms need this to breathe in water. So a fish doesn't have lungs, right? But water goes over its gills, and its gills has these little filaments in there that are like your lung alveoli. Whenever you breathe air in, you extract oxygen from that air by replacing, basically you do a trade-off with carbon dioxide, and then that oxygen can go into your blood and then travel to your cells where they need it for metabolism purposes, right? So fish are the same, except they don't have lungs. Instead, water goes across their gill filaments, and those gill filaments exchange oxygen for carbon dioxide. Oxygen then goes into their cells the same way that ours works, right? So do fish breathe? Yes, just not with lungs, right? They breathe with gills. So the amount of dissolved oxygen in water is really important, though. Ideal is 6 to 8 milligrams per liter. So for a fish to feel good, it's 6 to 8 milligrams per liter. Kind of like for humans to feel good, it's about 20% concentration or saturation within the air. If it goes too high, then you start to get lightheaded and dizzy, and you could eventually die of oxygen poisoning. Same thing for fish. If it gets too high, that could be bad for them. So we have some words for that. Anoxic means near zero. So that means A means not, or an means not, and then oxic pertaining to oxygen. So anoxic means that there is no oxygen. So it's near zero. Hypoxic, hypo means above. So hypoxic means that you are above normal. And then, I'm sorry, that should be below normal. Let me fix that. Below normal is hypoxic. And then hyperoxic would be above normal. So let me add that in here real quick. Hyperoxic would be above normal. And then remember that oxygen is a gas, so its solubility rules are different than most other gases. Remember, we said that if we increase temperature, we typically will decrease the solubility of a gas, which that is going to be the case with dissolved oxygen. But in terms of agitation, remember this is that big asterisk that you're supposed to put on there. If you stir up the water, typically that will allow more oxygen to dissolve, where most gases would not. So the two factors that affect dissolved oxygen, temperature. At high temperature, you're going to have low DO, which is dissolved oxygen, and then agitation. When water is stirred up, you will have more oxygen in that water. So that said, if you're presented with a choice, which one of these looks like it would have more dissolved oxygen? If we look at this, it looks like it is I don't know, for some reason it kind of looks cool. This place looks kind of tropical. I see some palm trees in the background. So if I had to guess, this would be cooler than this guy, right? So right away, this guy wins in terms of dissolved oxygen. It's a cooler stream probably, so therefore would probably be more dissolved oxygen in it. Now, the second thing at play is all of these riffles. This is agitation. The water is being stirred essentially by nature, right? Over here, it's nice and calm and still. So if we were looking at this guy would be getting agitation as well, which adds more oxygen to it. So this would be highly oxygenated compared to this higher temperature with no agitation. So if you're quizzed on that, there you go. We'll talk about another gas here in a minute because this gas is a good gas. But before we get there, we're going to talk about a bunch of other solution type stuff. So the first thing that solutions can do, aside from dissolved oxygen is when something dissolves in water. So when a solid dissolves in water, it can actually make the water cloudy, and that is called turbidity. So anytime something dissolves in water and causes it to become less clear or more translucent, transparent, opaque, right? Then that is going to be called turbidity. And if you think about this, turbidity is pretty important. If you're a plant, you need to do photosynthesis. Sunlight gets through the water pretty easy here, but it doesn't over here, so it can affect plant growth. Which, when we talk about plant growth, it can also affect little bitty tiny plankton, which are photosynthetic organisms, and they may not be able to do what we need them to do to contribute to the energy concerns within a lake. So turbidity is pretty important, and then conductance is another one. If we dissolve ionic compounds in solution, those then allow conductivity of electricity to occur. So what that means is there's an ionic balance within the water. If there's an ionic balance in the water, you need that to some degree if you're a living critter. If the water is perfectly pure, then that will actually draw water out of your cells, and then you would dehydrate, water would go into your cells if the water was pure, which then would cause you to swell up and bloat. And then if you were in a solution that has a lot of dissolved ions in it, then the opposite would happen. Water would get pulled out of your body, which would cause you to dehydrate. So this is, if you've ever heard of osmotic pressure, isotonic solutions, those types of things, that's what this deals with, which we'll talk a little bit more about down the line. So for right now, turbidity and conductance, these both can be measured in water columns. So you can put a device into water and determine what its turbidity is, and then determine if photosynthetic activity can occur. And then you can also put a little electrode in water, and you can decide if it would be too salty or not salty enough for certain organisms to survive in that as well. So then the other thing that can happen with solubility is we can see pollution. So water is a universal solvent. If pollutants get dissolved in water, water can then take it anywhere, and then we have an issue, and it's difficult to remove from the environment. So here, I'm not going to spend too much time on this. Pollution is basically man-induced change that causes the chemical, physical, or biological integrity of water to change. So it's basically something man did that then causes a problem for other organisms to live in that area, if that makes sense. The pollutant is the actual substance that causes that pollution. So man introduces the substance. So pollutant is the substance that causes that pollution. And then, like I said, if they dissolve in water, then that could cause problems. One of the biggest things that can happen is pH problems. So when you learned in chemistry about pH, I don't know how well your teacher went into this and how much you remember of this, but basically if something dissolves in water and produces H+ ions, that means that it is acidic. So essentially, if it makes a water compound or water-containing compound that has an extra H on it, now we're going to be acidic, and we'll talk about that in a minute. If it produces an OH, so if it pulls an H off of water, then that is going to be basic. And then how much H you have is going to be higher or lower pHs. So if you have high H concentrations, that's a low pH. And then if you have low H concentrations, that's a high pH. Acids are low, bases are high. And basically you don't really want to live in too far from neutral. So if you were to construct a pH scale, usually what I have you do is I have you draw a straight line, label that line A on the left, B on the right. Acids are to the left, bases are to the right, and then number 1 through 7, and then 7 through 14. So 7 is the middle. So acids are on the far end on the left, bases are the far end on the right, and then right in the middle is neither. So I tell people to put an N which actually stands for neutral. So 7 is a neutral substance. Now, if you were to look at the pH scale, you have hydrochloric acid way down here at a pH of 0. Then as you come up, vinegar is a 3, urine is a 5 or 6. Then as you get to pure water, that's a 7, which if you notice right there, that's pretty important. H plus, remember, is what makes us an acid. OH minus is what makes us a base. If you put H with OH, you have 2 H's and 1 O. You have H2O. So that is why pure water is neutral, because it has the same amount of H, which is what makes acids, and OH, which is what makes bases. So acids and bases react with each other and do neutralization reactions because they produce water and some sort of salt. So if you were here, I would show you what that would look like, but all you need to really know is that it's neutral when it's a pH of 7. Then egg whites are 8, so you're getting more basic now. Baking soda is 8. Baking soda is actually bicarbonate, which is similar to calcium carbonate, which is what makes coral reefs. So notice that if coral reefs are bases, right, and you get acid rain or acidic environments in the ocean, then that can actually start to eat away or corrode at, produce reactions with those bicarbonates. Anyway, so that's the acid-base scale. Acids are going to be harmful to life, and then strong bases can also be harmful to life. So the closer down to 7 that you are, the better it is for you. So let's take a look at carbon dioxide first of all. This has been a hot topic of conversation over the last few years when it comes to greenhouse gases, global warming, and all that good stuff. So let's look at it from what we've learned. At colder ocean temperatures, that means CO2, which is a gas, will be able to absorb better in the oceans, right? At higher temperatures, it's not going to absorb as well. So that means that if we're giving off CO2, basically for decades, people have said, well, that's okay, the ocean will absorb it and kind of act as our filter and clean it out, right? Well, if temperatures start to rise and we're still emitting CO2 at alarming rates, then at some point the ocean can't keep up. And at some point the ocean will not take in any more carbon dioxide. And then if the temperatures start to get higher, it might actually start to release some of that carbon dioxide, which would put more in the atmosphere. So CO2 is a greenhouse gas, meaning that when it's in the atmosphere, it causes sunlight to get trapped in the atmosphere a little bit longer, which heats up the atmosphere, and then surrounding things get heated up as well. So if we think about that, basically, if the ocean absorbs all that, then we should stay cool, right? But that causes two major problems when we look at that, right? The first is going to be this. When water does absorb that CO2, right? CO2 is what's called an acidic anhydride, which means that it's basically a dehydrated acid. So if you take CO2 and you add H2O to it, you get H2CO3, which is carbonic acid, okay? Carbonic acid is just slightly lower the pH, but it is an acid. And if you are something like a coral or a critter with a carbonate shell, which just most of the shells that you see like on the beach or seashells are calcium carbonate. What happens is you're composed of calcium carbonate, which is a base, or an anhydrous base. So what usually will happen is that H2CO3, that carbonic acid, will attack that carbonate structure and kill it. So basically it makes it harder for coral to create new coral, for critters with shells to create new shells, and it can even cause the death to ones that aren't fully formed yet. Then the second problem is this: if oceans start releasing CO2, that builds up more CO2, which is a greenhouse gas, which then causes temperatures to get hotter, which creates more CO2, which oceans can't keep up with and release more CO2, so it gets hotter. Oceans can't keep up, release more, gets hotter. You see the problem. That's called, we'll talk about it a little bit later when we talk about population dynamics, but that's basically positive feedback, which is a loop that basically compounds on itself. It's like compound interest, right? If you put in X amount of dollars, it gets bigger and bigger and bigger and bigger, and by the time you get to retirement, you have this huge chunk, right? That's positive feedback. That's the same thing here. As we make the problem worse, it makes everything else worse, which makes it worse, which makes it worse, which makes it worse, and then before you know it, global warming is a huge problem. So I'm going to stop there because that's basically talking mostly about solutions. We're going to talk a little bit about solutions and how that can affect density, but we're going to talk more about density as a whole in the next section of videos. So for now, this is all we'll talk about with solutions. So we started with just forming a solution and then what that can do environmentally based on what that solution has done in water. So we'll stop there. Next time we'll be talking about something else. And until then, remember, if you need help, hit that home button, email me, call me.